Thank you very much, André and Patrick, for the invitation. This is a very nice seminar, which I have been following, not every week, but whenever possible in the past, because there are lots of interesting talks already. And I'm happy to be part of this endeavor to spread news about input to state stability in this online format. So this is about ISS small gain techniques, which have been, I think, quite well known in this community for quite a while, starting in the 1990s, going on in the 2000s, and then particularly with the culmination at the end of the first decade of the 2000s with all these nice results about large-scale systems. And my observation was that this is a very nice technique, but probably not so easy to apply, because to really work with it practically in terms of Lyapunov functions, you really have to know a lot of things about your systems. And this talk is essentially about how neural networks can help with simplifying some of these difficulties or removing some of these difficulties. And as a side result, we can also do something about this, well, famous or infamous curse of dimensionality, which is, well, about many computations in control and also about computing Lyapunov functions. And I would like to tell a little bit about that. Okay, so what is the goal? I would like to compute Lyapunov functions for nonlinear ordinary differential equations, these ones here, or control Lyapunov functions when there is an additional control input in the system. Most of the talk will be on Lyapunov functions, but mainly because the extensions for control Lyapunov functions is quite easy. And this is why I can really make it as a more kind of appendix in the end and explain all the bit more difficult things for plain Lyapunov functions, which are easier to handle because they don't have the control input, right? So f can have a control or not. And I would like to first explain a little bit what is the outline of the talk. So this curse of dimensionality, what is that? Well, a curse of dimensionality describes a numerical method which has exponential growth of the computational effort, which could be either the computation time or the computation storage that you need, or both, in the state dimension. Right? The state in our case, let me go back one slide, is of course the x, which lives in Rn, and n can be really, really large. So, and then you have a problem. In fact, with the curse of dimensionality, the problem occurs usually not only when n is very, very large, but typical grid-based methods, I will talk a little bit more about that later, they already stop when n is equal to 4 or 5, and you can't really get much further than that usually. So this is the curse of dimensionality. And what is known is that deep neural networks are, under certain circumstances, capable of overcoming this curse of dimensionality. But this doesn't hold always, and I will talk a little bit about when it does and when it doesn't, but only for functions with certain beneficial structures. You need the right class of functions, then they can work very well. Otherwise, it may be just as difficult as any other approximation method. And the goal is now to detect and exploit such a structure for control Lyapunov functions or Lyapunov functions. This is where ISS and small gain theory will turn out to be very helpful. Okay, let me start a little bit talking about Lyapunov functions, what they are and why they are interesting. I assume that many of you know, but there may be some in the audience who don't. So let me spend a few minutes on what is this all about. So back to the ODE, right? No control for the first part of the talk. And let's assume you have an equilibrium, and we can always assume that it's the origin, because otherwise we can just shift the coordinate system. So this means that f vanishes in the origin, and whenever we have an equilibrium, of course, its stability is of interest. Right? And the Lyapunov function helps really in determining stability. And a continuous differentiable function v is a Lyapunov function if there are 3 k-infinity functions such that these 3 inequalities hold. So we have a lower bound on v, an upper bound on v, and an upper bound, but a negative one, on the orbital derivative, which means the derivative of v in the direction of the vector field. So in case you haven't seen these k-infinity functions before, these are functions which look as follows. So an alpha is a k-infinity function. If it's 0 and 0, strictly increasing, and unbounded, which you do not see on the picture, and of course positive elsewhere from 0, and continuous. So these are the k-infinity functions, and essentially what this means is that such a Lyapunov function essentially looks like what you see here. It looks like a bit like a bowl. So you have like a lower bound, which is this alpha 1. You have an upper bound, which is the alpha 2, and the Lyapunov function is in between. It can be less regular than this one. It can be like a bit more ragged or going up and down, but essentially it must be confined in a bowl. And what this inequality says is that the derivative, which is written here, so the derivative in direction f, looks like a bowl upside down, right? And these two surfaces, they touch exactly in the origin. This is what the inequality says. Okay, so this is a Lyapunov function. And well, let me show you a very simple example, which maybe all of you know. So this is the mathematical pendulum with some friction, which is indicated by K. So what this pendulum does, if you let it loose, it goes like this, right? It pendles and it gets slower and slower and eventually stops. No, it doesn't stop. It doesn't really stop, but it becomes so slow that it looks like it stops. So it converges to the downhanging position, right? And so here we have a typical solution. This is the position in the x1 direction, the velocity in x2. And if we start up here, the pendulum goes like that, and it spirals towards the origin and converges to that. And the Lyapunov function, for instance, if you can look that up in textbooks, it is given by this expression. And then if we superimpose the solution, you see that it goes down. Well, maybe not on this picture, but if you turn it a little bit, you see that really the solution moves down, like that, moves down and converges towards the minimal point of the Lyapunov function, so of the surface which represents the graph. So that's what a Lyapunov function is. And the question is, why is it interesting to have a Lyapunov function? Well, first of all, if you do not know whether the origin is asymptotically stable, Lyapunov functions provide a certificate for that. If you can find a Lyapunov function and show that it satisfies these three inequalities, you can be sure that the origin is really asymptotically stable, so that all solutions which start close stay close and converge eventually to this equilibrium. But you can do more. Asymptotic stability you can sometimes also check via linearization, but what you do not know by linearization is for which initial conditions do the solutions converge to the equilibrium. And this is given by the level sets of the Lyapunov functions. They are always subsets of the domain of attraction. So you can estimate the domain of attraction if you know Lyapunov functions. Well, then they give information about robustness of stability. So we will see something particular, ISS Lyapunov functions later, but also plane Lyapunov functions already tells you, well, if you have this negative orbital derivative, if you perturb your vector field a little bit, it will stay negative, right? Simply because this is an open condition. And that means that a little bit of robustness against perturbations is always present if you know a Lyapunov function, and you can actually use the Lyapunov function to quantify how much can I perturb the vector field so that I can still see the solution going down. In case of control Lyapunov functions, there is much, much more to it, because then these really give you the possibility to design stabilizing feedback laws. And I will talk a little bit about that when we come to that in the last part of the talk. Yeah, and then I'm interested very often in optimal control. André already mentioned I'm also doing model predictive control. And one tool for doing optimal control is the Hamilton-Jacobi-Bellman equation. And eventually, this is where we would like to go in this research. And I will tell you a little bit in the end where we are at that point. So in that sense, the Lyapunov functions and the control Lyapunov functions are a step towards something which is even more complicated and requires even more sophisticated techniques. Yeah, so all these reasons have motivated a lot of research for computing Lyapunov functions. And since it is difficult to compute them analytically very often, of course, numerical methods have been developed. And here's quite a lot of these. So we have series expansions. We have what is called semi-Lagrangian schemes. This is what I also did about 20, 25 years ago. We have finite elements combined with linear programming by Ziggy Hafstein. We have sum of squares by many people who do that. We have radial basis functions. And if you are a little bit acquainted with that, then you would know that semi-Lagrangian schemes, finite elements, radial basis functions, these are all techniques for solving PDEs. And the reason for this is that essentially you can take the third inequality that we had, call the right-hand side capital W, and write this down as a PDE. And this is what is called a Zuboff type PDE, was studies in the 1960s, is actually quite related to the Massera construction of Lyapunov functions, for those who have heard about that. But it had this additional twist that we have this PDE characterization, and Zuboff particularly characterized the solution of these PDEs. And many of these schemes, they really use PDE, numerical PDE techniques to try to solve this equation. I will come back to that in a couple of minutes. What all these methods have in common is the curse-of-dimensionality. And for finite elements, it's quite easy to explain why this is the case. So finite element uses a grid with grid points. And suppose you need a certain distance between two neighboring grid points to get desired accuracy. Well, if you have a one-dimensional system, then of course the x comes from a one-dimensional set, say for an interval, and say you need 10 points to cover that interval with sufficient accuracy. If you have a two-dimensional problem, then you have a piece of a plane, right? A rectangle, for example. And then if you need 10 points in each direction, then to cover everything, you need 10 by 10 points, which are 100. If you have a three-dimensional problem, you have a cube. It's 10 by 10 by 10, it's 1,000. 1,000 in 4 dimensions, 10,000 in 5 dimensions, 100,000 in 6 dimensions, 1 million. And you immediately see how quick the number of grid points that you need grows if you don't do it cleverly. And this is precisely what causes the curse of dimensionality, right? And this happens for the grid-based methods here, but this also happens for sum of squares and series expansions methods where the number of coefficients simply grows exponentially if you have more and more components in your vector x. And this is precisely the reason why these methods do not carry over to high dimensions. And not high, in this case, can even mean 5, 6, 7. This is usually the bound where most of these methods simply do not work anymore, or you have to wait so long or use such an expensive supercomputer that this doesn't really pay off. And the question is now, can deep neural networks do better? And yeah, the question is really whether they can do better from a theoretical point of view. I will also show you some computations, but I think that the main originality of what I'm telling you lies in the theoretical analysis. But I will explain that. So deep neural networks. I assume that here in the community, there are not so many people. There's a question in the chat. Let me answer that immediately. What is the W function in the PDE? Well, I've written it in the way that Zuboff wrote it with this W, but what it actually is usually is simply, if you design it, if you go back to the definition, it's exactly this minus alpha 3 of norm of x. You call this minus W, and then this is the W. But you can do more complicated things. So it doesn't need to be of that form. This is why I called it W. But essentially, if you come from here, then you would use exactly this alpha 3, right? So I hope this answers the question. Okay, good. Let's go back to where I was. So here we are. There we are. So yeah, so it's definitely not a new idea to use neural networks to compute Lyapunov functions. And this already was in the, should I say, first or second wave of neural networks in the 1990s, where these were fashionable for quite a while. This has been done. Here's a list, possibly incomplete, of people who worked on that. Very interesting, by the way, that Eduardo Sontag worked on that also in the 1990s. And I will talk a little bit about training the neural network later, and I do not claim any originality in what we did there, because some of these ideas were already in a quite similar form there in one or the other of these papers here. But what none of these papers does, and I think what I and then my co-author Mario Sperl, whom I actually did not mention at the beginning, so he's my PhD student, and I did, is the complexity analysis. I think this is really the new thing that we did here, and this is really something which is different from all the previous works. Okay. Yeah, so here's the neural network, and it's a neural network with 2 hidden layers, so it's not very deep, it's just a little deep. So deep would be something with, I don't know, 10, 20, 30 layers. It's medium deep, but it's also not shallow, because shallow means just 1 layer, so we have at least a little bit more. What is a neural network? A neural network, in our sense, is simply a device to store and express a function. And let me start from the bottom. This function that we want to store should eventually be an approximation for the Lyapunov function. Yeah, this function depends on a lot of parameters, theta, a vector of parameters. So these are all these w's, b's, a, and c, which are in here. I will explain in a minute what they are. And the training then simply expresses or means that you use optimization to get the best vector, so that this function that you express with the network best approximates the Lyapunov function v, right? So the theta star would be the best parameter vector. Well, usually you don't get the best, but something which is very good, right? Now, how does this neural network work? How does this represent a function? Well, what you do is you have the input here in my picture, the lowest layer, which depends on the components of the state vector, x1 to xn. And then what you do is you send them all into these neurons here. And what happens in each neuron? Well, each neuron is just a storage for a single scalar value. You take the x, you multiply them with a vector of weights, then you get a scalar. You add a so-called bias term, and then you have a scalar value here depending on your input x, and you process this with a certain function sigma 1, which is called an activation function. This could be as simple as the identity, which is here. Very popular is this ReLU. What we used, because this turned out to be better for our purpose, is this called soft plus function here, which is essentially just a smoothened version of the ReLU. So the ReLU looks like that. So it's like this hockey stick function, this max of r and 0. And this soft plus, this logarithm of e to the r plus 1, is simply a smooth version which doesn't have a kink here, but goes smoothly and asymptotically follows exactly this ReLU function. Okay, so this means by this operation, you have now a scalar value in here, and then you again build such a combination exactly the same way to build a second number of values. So this is this yk2, a second vector of values, with new weights and a new bias term. You get new values by putting these into sigma 1 and processing them. And then in the end, you combine everything finely linear with this vector a and this another bias term c to get the function w. Yeah, and now the idea is that you choose the w's, the b's, the a, and the c such that what comes out here approximates a Lyapunov function. Okay. What can these things do? Yeah, what is known since the late 1980s is that actually every continuous function can be approximated arbitrarily well by a deep neural network. And this is called the universal approximation theorem. That sounds great, but there's a problem, because what is also known, and this was also investigated in the 1990s already, is that the number of neurons that you need for that needs to grow exponentially with a dimension n. So you just by using neural network instead of something else, like a grid-based or interpolation-based or expansion-based method, you do not beat the curse of dimensionality. There's no way around that so simply. But there are certain function classes where it is known that they work very well. And one of these function classes are functions which are very smooth, have a high degree of smoothness and suitable form of, like, for example, the Fourier transformation. Certain assumptions on the Fourier exponent, coefficients need to be satisfied. Barron functions, if you want to look that up, is one class of these functions. And they have been actually quite successfully used for solving certain equations. For example, also Hamilton-Jacobi-Bellman equations, which are related to this Lyapunov PDEs, but for second order. And the reason for this is for second order equations, you can really expect a lot of smoothness. But for the problems that we have in mind here to solve, deterministic problems, particularly for control Lyapunov functions, there's no chance to expect that they have this degree of smoothness. And even if they are smooth, I mean, smooth is not enough. They also need really have a very particular form of the Fourier transformation. You can do that for certain classes of second-order equations, but you can't do this for these problems that we have at hand here. So second-order equations always correspond to stochastic problems, and the noise that you have there tends to smooth everything out. In the deterministic case we have here, this is not true. So let's look at a different class of functions. And the different class of functions I'm looking at here, in which we are using, are the so-called compositional functions. Here are some references. This is a paper by a couple of computer scientists where I learned about this concept. Wei Kang and Qi Gong, they have used this concept in already in context of optimal control in several papers. And there's also a very recent paper of Wolfgang Dahmen, who investigates this as an general approximation architecture. What are these functions? These are functions of the following form: nested functions, which are all low dimensional, but due to their nesting structure, they get a certain complexity, right? So each function should be low dimensional, but you can have many of them, and you can have them nested in this way. I want to do it even simpler today. I would want to look at a very special subclass of these compositional functions, and which are these separable functions. And this simply means that we write a function, in this case our Lyapunov function that we want to compute, as the sum of low-dimensional functions. So Zj are subvectors of our big state vector. And the subvectors here, they are they should be of a certain size. Actually, this is a typo here. This M should be this dj, so the number of elements, and they should be bounded independent of n, or at least not grow too fast. This can be allowed. And S is, of course, then the number of these lower dimensional functions, and this should be bounded by the space dimension. Yeah, so these are the separable functions. And before I want to go how we get them, I would like to explain, why are they good? Why are they beneficial in deep neural networks? Well, the reason is the following. The network you can write down is this one. What we do is here, we do have one layer, which essentially does the splitting up of the vector into the subvectors. And then we have these gray blocks. We have S of them, one for each of these Vjs, here for one for V1, then the others are not shown, then Vs here. And now if the dimension grows, right? So first of all, we can approximate the individual function by these blocks, and then they are added up to the final function up here. When the dimension grows, the number of these gray blocks only grows linearly, right? And not exponentially. So the number grows linearly. And now if the dj's, which are the input dimensions here, if they are constant or maybe grow very slowly, this would be okay. And the number of neurons that you need overall also grows, well, linearly plus a little more. And if you control this growth, then it's definitely below exponentially, typically polynomially, even polynomially with a quite small exponent. So something like squared or cubed, but not more, right? And this means if you have this structure, and this is important, the dimension of the Zj do not grow too fast with the overall dimension, then you can really beat the curse of dimensionality and can express these functions with only a polynomially, with low degree, growing order of neurons, and then also of computational effort. And actually what you can do here in this first layer, you can actually do something much more complex than simply splitting up the X into the Zj. You can actually do much more complex transformations, and I will talk about how we can use that in the very end in the outlook. I won't use it that much in this small gain based idea. Okay. Let me go to small gain theory. I'm not sure how many people here know it. It's an ISS seminar, so I assume some familiarity with ISS, but I will nevertheless explain from scratch the idea behind this small gain theory. So what we do is we do not only decompose the X into the Zs, but we also decompose the F, our vector field, in the same way, right? So we decompose it into F1, F2, up to Fs, and the dimension is simply corresponding to the dimension of the subvectors that we have here. So Z1, Z2, Zs. And then what we do is we can write the vector x as just the vector Z1 plus the vector Z minus 1, which is essentially everything but Z1. So Z minus I is all the rest corresponding to Zy. And then I can formally, by a slight abuse of notation, the whole system, I can write that as a collection of subsystems which are interconnected via this Z minus I here, right? So the Z minus I describes how the other subsystems influence the subsystem for Zi. Okay, so this is a decoupled system, or a system of decoupled differential equations of lower dimension. And let's for the moment assume that the FIs are decoupled, so that each FI does not at all depend on Z minus I, it only depends on Zi. And then you see immediately that you can compute low-dimensional Lyapunov functions separately for all the individual Fs, and then just add them up to get a compositional, or actually separable Lyapunov function V via this formula. And it's a simple computation that shows you that this is indeed a Lyapunov function for the whole system then. The trouble is that, of course, dynamical systems and ODEs are hardly ever decoupled, so you cannot expect this really. But somehow this shows the way how small game theory works, because it somehow generalizes this idea without assuming complete decoupling, but rather something like a certain kind of weak coupling. So let's look at this equation again, now with the Z minus I. And well, if they were decoupled, then you could assume that we have a Lyapunov function like that, right? If you just plug 0 in here. So this is the usual inequality that you need for Lyapunov functions. If they are not decoupled, you would now plug in something in here, which of course would cause something to appear on the right-hand side. And well, the right-hand side should be negative, but of course you can't expect that if you plug some values in here that the right-hand side will remain negative. There might be some positive terms popping up, and these positive terms, we write them in the following form. And we assume that we can find Lyapunov functions which satisfy these inequality for all subsystems Fi. And these are so-called ISS Lyapunov functions, right? And then we have certain values, functions actually, scalar functions, alpha I and gamma ij. And the alpha I describes, as before, the decay of the Lyapunov functions, or the negative derivative. And the gamma ij, they describe the coupling of the systems among them. And now I'm simplifying a little bit, and I know that there are experts here, so please do not be too harsh with me. Essentially, what the condition can be written down is that if in each cycle, if we look at the graph that describes the interconnection, so this is a directed graph which basically has an edge whenever system I influences system J. And then we look at all the cycles in this graph. And if all the cycles, along all the cycles, we have this condition here. And again, you need to be a bit more careful maybe at some points, but essentially it means that all the interconnection of the gammas, the concatenation of the gammas along a cycle, are all in all less than the identity, which means that not all of them need to be small, but some should be small. And if some are large, then the others need to be even smaller to satisfy this condition. But it's a trade-off, right? Some can be large, some can be small. Overall, they should satisfy that. And then it's known that a separable Lyapunov function exists, and there are many different constructions. The one I'm referring here to is from this paper by Daszkowski, Ito, and Wirth. But there are other constructions. I'm mentioning this one here. I'm actually mentioning Björn Rüffer's PhD thesis where first constructions were in there. So there are many different ways, and there are also different conditions. There are different ways of writing ISS with max instead of plus. This is just an example how you can see how this low-dimensional structure appears, right? By decoupling and assuming that the interconnection is, in a sense, weak enough. Yeah, so this gives us a condition under which a high-dimensional control Lyapunov functions can be written as a sum of low-dimensional functions. And what I already said a while ago is that the most difficult part is now to determine the appropriate subsystem structure. This is exactly what the lower layer here can do. So this really can determine the structure that we need in order to get these low-dimensional functions, right? So how to split up can really be learned by the by the neural network. And as already mentioned, it can actually do more. It can do more complicated transformations. So it need not be that we only split up the axis here, but it could actually be that we make a linear transformation, for example, or even a nonlinear transformation. The theorem here is for linear transformations. So what we assume here is that we have this separable structure, but a bit more involved. We allow for linear transformations here. And now that what was the dimension of the subsystem before is now the rank of this transformation. And if we assume that such Lyapunov functions exist, where this rank here, d max, is independent of n, then they can indeed be approximated with any accuracy epsilon with a number of neurons that grows only polynomially in n. So you can really prove that if such separable Lyapunov functions exist, then you can beat the curse of dimensionality with deep neural networks. And again, we have small gain theory as a justification for this method because it ensures the existence of such a function. But we neither need to know how to split up the system, nor do we need to know the VI. This is all learned or trained or whatever, or computed by the neural network. Well, actually by the training process of the neural network. So, and if we can really provide an appropriate training algorithm, then this should work. And this is now the next part. How do we train the neural network to really compute Lyapunov functions? Yeah, so the basic algorithm for training a neural network is we define a loss function, which kind of penalizes the deviation from what we want to have. We choose a test data set. In our case, these were just randomly generated vectors from a certain compact subset of the state space. And then we use an algorithm to minimize this Monte Carlo-like expression, right? So the L at the test points, right, with respect to the network parameter theta. And what you already see is this is a little bit unusual for training neural networks because we have the W, so the outcome of the network, but also the derivative of W with respect to X here in the loss function. And we need that, of course, because in the defining inequalities of the Lyapunov functions, we also have the function itself and the derivative, and of course the state. Yeah, the choice of the loss function that we have done is basically inspired by approaches for solving PDEs with neural networks. There's a long, well, not a long history, but a long list of papers since about 5 years ago when this started. So many, many people have done this for different classes of PDEs. And well, since this is motivated by PDEs, let's start with a PDE. Let's start with a Zuboff type PDE. Now I have really the alpha 3 here instead of the W, and try to design a loss function which gives us a penalization value whenever this is violated. Well, this is not enough. We also, of course, need the boundary conditions of this type. And then what we do is we choose the loss function such that it penalizes all the violations. So if P is the gradient here, then this first term would penalize the violation of this equality. And these terms here with the minus and the plus, which are the negative and the positive part, they penalize the violation of this inequality here and of that inequality here. So whenever we find a test point where either this equality here or the inequality here or there is violated, the loss function gives us something positive. And since we want to minimize that, the training algorithm is trying to minimize, trying to find a theta value where this is where the network satisfies this equation and all the inequalities. Now here's a problem. This is how we started because of this Zuboff type PDE and this PDE approaches that we found in the literature, but it soon turned out that it's known that a Zuboff solution always exists for appropriately chosen alpha 1, alpha 2, alpha 3, but it may not be compositional, right? So it may be existing, but it may not be of that form because we don't know the right or the correct right-hand side for the Zuboff equation to get this compositional form. So even if a compositional Lyapunov function exists, it may not be the solution of the Zuboff PDE. So it may actually be better to use for the training something which is more adapted to the original task. And this is precisely, well, we do not want really a solution of Zuboff's PDE. What we want is a solution of which is a Lyapunov function, so which satisfies these three inequalities. And we can easily code that into the function by just putting this plus here. So it's all the same as before, except that now we only penalize the violation of this inequality, but not the inequality. In other words, when this derivative here, so this p times f is very small, we don't care. That's fine. That's good. It's even more negative than we maybe need, but only if it's positive. So if it's larger than this alpha 3 or not negative enough, then this penalization term gives us something positive. Okay, let us see how that works. This is the network structure and the program I used. This is already, these were the first attempts. We compute everything in the unit cube, and the optimization is terminated when for all the data points that we used, we have this, well, an error of less than 10 to the minus 6 in the loss function. And this optimization is done by a standard method in neural network training, the so-called Adam optimizer. I'm not saying more about that. This is a standard tool that you have in this packages like TensorFlow or PyTorch. Okay, let us start with something very simple. And all the ISS experts will immediately see that this is a cascade of two ISS ODEs to one-dimensional. So it's ISS. It satisfies the small gain theory trivially. So we know that there is a separable Lyapunov function. And we can actually compute it. It looks like that, right? Well, actually, it's not the only one, but this is one that satisfies it. But what is important is that we really need some higher order terms than just squared. So it's a completely standard choice, x1 squared plus x2 squared will not do the job for this system. And yeah, we trained this network with this inequality loss functions. All the alphas here were chosen as quadratic functions. We had two sublayers which really looked for two one-dimensional functions, so really like this one and that one, and 200,000 test points for training. And then what we get is this. It looks very nice. It's a bit flat in one direction, but this is what we get. And if you look at it from the side, you'll see that it really does what a Lyapunov function should do. We have the function here. We have the orbital derivative by this net, and the one really goes up and the other one goes down, and they touch exactly in the origin, just as we would like to have it. Computation time was 48 seconds. What happens if we try to enforce this equality by this term, so no plus down here? So we really try to enforce this Zuboff equation solution. Well, it doesn't work in that case, because you can immediately see that this function that we know to exist, this separable function, has a form which does not have a derivative which is like that, because of this x to the power of 4 term, or x2 to the power of 4 term that we need. So this doesn't work. Convergence could not be reached, and what we got out of the network does not represent a Lyapunov function. Well, from here it still looks kind of okay, but if you turn it, you see that, well, this is 0 at the wrong point, right? So the minimum sits at the wrong place. This gets even positive here, and also the maximum is in the wrong place. So it's really not a Lyapunov function at all what we computed. So this really shows that the structure that we have determined really matters. And it really only works, this approach, if we have the separable form. Okay, how high can we try? Well, frankly, we don't know. We don't have a supercomputing group here who does this, push these things as far as we can. But at least we tried a 10-dimensional example. Here, this is an example where you can actually see that the small gain condition is satisfied for 5 two-dimensional subsystems. So we're looking for a structure with d max equal 2. So these gray blocks have always 2 inputs in the neural network. In order to make it not so easy for the neural network, we put this coordinate transformation, which is randomly generated around, so that really the structure cannot be seen. So if you write down what comes out of here, write down this right-hand side here, it really is a mess. So with the human eyes, you don't see any structure at all anymore. But the neural network is really able to find that. This is, of course, now a projection into a certain plane, more or less arbitrarily chosen. And you see that it very nicely gives you the structure that you want to have. The function goes like that. The derivative goes like that. And what is interesting is that while our theory does not guarantee that we really get a Lyapunov function, we only get an approximate The figures suggest that this is really a true Lyapunov function, except maybe in a small neighborhood of 0. So we can't be that sure here whether it's really completely okay, but everywhere else this is really fine. And if you evaluate the function along numerically generated solutions of this 10-dimensional equation, you see it really does what a Lyapunov function should do for different initial values. It goes down monotonically to 0, so it really looks pretty good and what we want to have. But no proof so far, and it's actually also not clear. I discussed with several people how such a proof would work. Okay. Now, as I said, control Lyapunov function is merely a small appendix to everything because things are so similar and we do not need to really change a lot. What changes here is that we do not want this derivative in direction of f, so the derivative along the solution, to be negative for all u. We only want it negative for some u, and this is why we put the infimum here, right? So the infimum over all u should be negative, less or equal this minus alpha 3 norm of x, which essentially means that if we pick the right value, and this actually would be the value you also wanted to pick if you want to control the system, then you get downhill and then you approach the equilibrium. And you can use this inequality then to generate feedback laws in various ways. You should do some regularization, maybe some discretization there to make it work nicely. But this is essentially what you can do to what you can use to then define a control. And the question now is, when can we employ small gain techniques here? And there's a nice answer given by a recent CDC paper. So remember, this was the condition that along for each cycle in the graph, we want to have this inequality satisfied. And basically what this means is if in each cycle of the graph, there is at least one subsystem for which this gamma can be made as flat as we wish. And these kind of subsystems are called active nodes in this paper by Chen and Astolfi. Then there exists a control Lyapunov function of the separable form, right? And made arbitrarily flat, of course, means by some controller, by some feedback law that we implement in the subsystem. So, for example, if we look at this graph and we look at the subsystems, all denoted by their state vectors, then we see a cycle here, for example, we see a cycle here, we see a cycle here disconnected from the rest, another cycle here. And if we now assume that all these blue nodes are active nodes and we can make the gamma as flat as we wish, then the condition is satisfied and we find a separable Lyapunov function. Here's a concrete numerical example, much simpler. Now the subvectors are simply one-dimensional, so Z1 is just X1, Z2, X2, and so on. If you look at this system, you see that X1 is influenced by X3, so there should be an error over here. X2 is influenced by X1, so there should be an error here. X3 by X2, so an error here, and so on. So the graph would look like that. You see there's exactly one cycle, and in this cycle you find in particular this node X1, and here we have this plus U, which means we can make the convergence as fast, the convergence to 0 by using here a controller, as fast and as robust with respect to this X3 as we wish. So we can really make gamma ij as flat as possible, which means that this should work. And in fact, it's not only the theory that tells us, but also the computation that this works. This is again a projection of the resulting function. You see that now, due to the infimum, this derivative is not very smooth anymore, right? We have these kinks in there because we have these derivatives, but we see that it very nicely gives us what the Lyapunov function should look like. So yeah, this works too. And this brings me to the end of my talk and a little bit of summary and outlook. So what I explained to you is that deep neural network can be used for computing Lyapunov functions and control Lyapunov functions. And I think I already mentioned that this is not a new finding and not our main contribution, right? So maybe our algorithm has some special structure, but the basic idea is actually pretty old. Yeah, if the approximated function has a compositional structure, and in our case, particularly a separable structure, then the method can provably overcome the curse of dimensionality. So no exponential growth of numerical effort, of storage effort, of number of neurons or whatever. And in that case, we can actually handle dimensions that are far beyond those feasible for grid-based methods. And I showed you a 10-dimensional example, which is actually far beyond, because in grid-based examples, for what I know, 3 or 4 is really the maximum that you can get in terms of dimension. Yeah, small gain theory describes a situation in which a compositional Lyapunov function or control Lyapunov function exists. So this gives us a kind of justification that we could try this method. And well, what is still to be done? Actually quite a lot. So the current work and future work consists, for example, of exploitation of the transformation T, which I have not really done. So far I talked about small gain, which is just splitting up the vector. Now actually we can do more. And from this we can actually show that separable control Lyapunov functions exist for linear stabilizable, and in local form, even for linearly stabilizable. So these are linear systems which are stabilizable. These are systems which are stabilizable by a linear feedback, and also for feedback linearizable systems. So you can really exploit this transformation to find other structures in addition to the small gain structure that I told you about. But I should say that for this, at least for the proofs that we have at the moment, that we are about to work out and publish soon, no ISS theory is needed. So unfortunately, this doesn't really fit into this seminar here. What we are doing also, and we have a first paper submitted to CDC, is an extension to optimal value functions, so really to solutions of Hamilton-Jacobi-Bellman equations, or in discrete time Bellman equations. And our first idea was to simply take what we have and use the theory that we have developed for control Lyapunov functions for so-called super solutions of the corresponding equations. Because essentially a Lyapunov function or a control Lyapunov function can be written as a super solution of a Hamilton-Jacobi-Bellman or Bellman equation. Trouble is, we have not found a good way so far to control the quality of the super solution. So super solution means it's larger than the true solution, but the gap can become arbitrarily large. But what we have found out is that under certain conditions, which are not too optimistic to expect, we can actually overcome this problem by looking at not separability, but what we call overlapping separability. This means that the variables do not only appear in one of these functions in the sum, so in the v1, v2, v3, but some variables appear in several of them. Just the number that at most appears is still bounded, right? So we have this overlap. Certain parts of the state vector appear in several functions, but overall the number of components is bounded, and then we can actually show that this also works. We can construct a network which approximates that. And we can also show that by making some assumptions on the sensitivity, we can really get this overlapping separability and get this approximation. So this is just submitted. Again, this is without ISS theory, unfortunately. And now here's something that is really an open problem. Despite the fact that many people have done that, it turns out that training neural networks for control Lyapunov functions is a really difficult task. And this is because we have to look for essentially for this infimum over U, or if you wish, the controller that does the job, and the Lyapunov function simultaneously. And since you have to do that, you really need some quite sophisticated training algorithms. What we have found out is that it's really difficult to get this thing converging. If it converges, it's quite quick, but you really need to tune a lot of parameter before it eventually works. It's much different from what I'm used to from numerical analysis from my earlier work, where you usually have schemes that converge very, very reliably and also quite fast. Here you have stochastic methods, you draw samples, sometimes it converges, sometimes it doesn't. And we are really looking, and now also with the help of certain undergraduate students who are doing their thesis and practical internships on that topic, we are looking for more efficient training algorithms. And even though we do not want to go into high-end computation, at least we would like to have a couple of nice examples. And this is what we are working on at the moment. Okay, I think that was it. And I thank you very much for your attentions. And if you have any questions, please let me know.